Overfitting, overfitting, overfitting. That is indeed a curse. For any machine learning algorithm, including decision trees, that is indeed a problem that we want to learn how to fix. So many times it has happened that I've listened to friends who have been complaining about certain algorithms that they've been training, but the general problem was that during training the algorithm was just doing absolutely amazingly. The error was just going down and down, but when it came to the actual testing on the unseen data, the algorithms just did disastrously. And now that is a common problem called overfitting that we're going to talk about today, specifically for decision trees. So if you're ready, I am as well. Let's dig in. Right, so before we understand what the idea of overfitting is, I just want to ask you a couple of questions. These are very important. Now, imagine that we have the task of classifying images of cats and dogs, meaning that if our machine learning algorithm is trained properly to recognize and discern between cats and dogs, I want to give it a new image that it hasn't seen before of a cat or a dog, and I'm expecting the machine to classify that image correctly under either of the categories. Okay, now two important questions here. Number one, if that is my task, what is my population? Now, what do I mean by population? Population means what I'm gonna use to sample my training data from, okay? Or the training data that I have at my disposal has already been sampled from a much infinitely larger population. Now let's be more clear here. Now imagine that this big weird shape represents my population. What does it mean? What does it contain? It contains all the images of cats and dogs. And when I say all the images, I mean literally all the images that have ever existed and exist in the world. So that is the population of the data out there, okay? However, it's literally and practically impossible for me to use all the data out there in the world to train a machine learning algorithm, right? So that is why we deal with training data, meaning that we sort of sample, or maybe we don't do that ourselves, but the training data that we have at our disposal has already been sampled from the population, meaning that if that is my population, the training data is extracted from the population. So we call this bit the training data. So training data would be some images of cats and some images of dogs. It might have images of certain breeds of cats and certain breeds of dogs, but not all the breeds out there. That's very possible, right? So the question is the training data that I'm going to use to teach my algorithm what image represents a cat and what image represents a dog, is this training data a good representative of the real population out there? Now, to answer this question, imagine that my training data covers maybe this part of the population and that part of the population, and that's it. So this part and that part. Let's say it covers certain breeds of cats and certain breeds of dogs and their images. Now, the question is, let's say I trained my algorithm with this training data. So these two parts are my training data. Yeah? Now, my machine has been trained. This is my machine, the trained machine. Now, my question is, if for testing, I ask my machine about a new image of a cat or a dog, will it be able to correctly classify that? Now, obviously, if that image falls somewhere around here or here in the subsections, in the subsets, that my algorithm has been trained with, well, then the machine will learn, will know how to classify that, and it will classify it correctly. That's fine. However, what if that data happens somewhere, say, around here? If that is given to my data, to my machine, will the machine be able to classify that correctly? Now, that is something that we don't know, and that is the big question. Have I trained my machine in a good way that it can generalize what it has learned from these regions, these two regions? Can it generalize its knowledge to all the other part of the population? Yeah? It's as if you're teaching a little kid how to sum two numbers, and you show the kid many summations of two numbers, and then you can't possibly show all the possible combination of summation of two numbers to a person. That's clear. But the question is, if I show that kid two new numbers, can he or she still sum them and come up with the real answer or not? Can he or she generalize what they have learned from summing two numbers to the unseen test numbers or not? So to summarize, these are the important questions. Number one, what do we want at the end of the day? At the end of the day, we want to fit our model to our training data. Okay. Now the question is, how well should we fit it? So we have some sort of a measure, a quantitative measure of error that can tell us how well are we doing on the training data. So the question is, how well are we allowed to learn how to classify the images in the training data? Do we want the lowest error possible? Do we want the error of 0? Actually, most of the time, almost all the time, no, we don't. And why the hell not? I will explain to you in details why not, but the short answer is, if we do absolutely amazingly great on the training data, it means that we have ended up memorizing the training data. So it means the only things that I can recognize as a cat or a dog, the only images are the images, literally the only images that are in my training data. Any other cat images, any other dog images, I will never, ever, ever, ever recognize them as either cat or a dog, because I've memorized my training data. I haven't fitted to my training data. I have overfitted to my training data. So we are looking for a good fit, okay? Not an overfit. Because if you overfit, we have this thing that I'd like to call the lack of generalization. Because the ultimate goal is to make our machine learning algorithm to generalize its knowledge that it's earned from the training data to the unseen test data that could come from anywhere from the population area that I just showed you. So let me tell you exactly what I mean by memorizing the training data. Right, meet Tom the cat. Let's say we have many images of cats, but not just any cat. It's exactly one cat called Tom, Sir Tom. All the images are from this particular cat, but from different angles and different places with different background. Okay, now the goal is to train our machine learning algorithm to recognize, say, a cat. Okay, let's simplify that, just to recognize a cat image. Now, let's say we have finished training our model. Now we want to test it. Now, during testing, we have one image of Tom that the machine hasn't seen before, and one other image of some other cat called Liz. And we want to test our algorithm. Has our machine learning algorithm learned the concept of cat? What do you think will happen? It will recognize Tom as a cat, but it will recognize Liz as not a cat. Yeah? because all it knows, all the machine learning algorithm knows about the concept of cat that is going to learn is that cat is Tom. That's all. Nothing else can be a cat. And because our algorithm has learned the concept of cat on our training data, on the Tom images, perfectly, with zero error, because of that, it has memorized what makes a cat. It has memorized that only Tom can be a cat. So it can never, ever generalize its knowledge to new images of other cats, and it will just reject them, and it will label them as not a cat. So we can say that it has actually overfitted to the training data. Yeah, so as you can see, it's not a good idea to do absolutely great on the training data, because in this case, for example, our training data is very limited. It has only images of one type of cat, or actually just one cat. But we want to have a variety of images of many different types and breeds of cats. But in this case, our training data is absolutely ridiculously limited. So in our previous case that I showed the population of our data, so here the population is images of the cats, and here our training data is maybe this part, very small, of all the possible images that are out there, nearly zero. I mean, it's just too ridiculously limited. So learning this bit of the whole population perfectly means that we are inflicting misery on ourselves, because it will have, my algorithm would have absolutely no knowledge about the other parts, and it has no way to generalize its knowledge that it has gained from this little teeny tiny part to all this other parts, to all the other green regions that contain images of many different types of cats, and our algorithm would just fail miserably. So, in summary, the generalization has failed. Our algorithm has failed to generalize its knowledge to the unseen data. Yeah? And why did that happen? It's because the way our algorithm now understands the concept of cat is very bad, because the perception of our algorithm from a cat equals Tom, because it has overfitted to our training data. Now, what we want is a better perception, a more abstract perception of the concept of cat. Like in this little picture that you can see here, over here, it resembles a cat, you see, but you can't really figure out what cat is that. Is it Liz? Is it Tom? What breed is that? As you can see, it is a very general, or you can also say abstract description of the concept of cat, which is great. So this right here, like a sort of round face, 2 pointy ears, 1 tail on the back, 4 paws, that can basically contain so many different types of cats images. Yeah, so that is a far better perception of the concept of cat than Tom, clearly. Now this is good. Now this is a perception that can, and it's a knowledge that our machine learning algorithm can generalize to the unseen data. So that is what we're looking for. We don't want to overfit to the training data, okay? So where did it all go wrong? It all happened in the training data. You see, doing great on your training data can destroy your generalization power to the unseen data in 2 cases. Number 1, if your training data is insufficient, meaning that it is a very small subset of the population, doesn't have much variety, doesn't have a large size of samples, so very teeny tiny limited sample set that doesn't even represent the actual population. And number 2, you might have a good, big, large set of training data, but it might be noisy. Yeah? For example, you might have pictures of cats that have been labeled by mistake as dogs. and you will show that picture to your machine learning algorithm and you say, by the way, this is a dog. So that will confuse your machine learning algorithm. Okay, so in these two cases, number one, your machine learning algorithm will, if it overfits, it will overfit to insufficient training data. It will memorize a very limited subset of training data, and obviously it will fail to generalize this knowledge to the whole population, to the unseen data. Number two, if the training data is noisy, it will learn the noise. Okay, I mean literally, it will learn the noise. Okay, for example, it will learn pictures of cats as dogs, okay, which is wrong, right? So imagine if your algorithm does perfectly on a noisy data set. Okay, now imagine a new data comes in. Of course it's gonna fail, okay, because it has learned the wrong thing perfectly. Okay, so in this case it means learning the wrong data perfectly, and in this case it means learning the insufficient data perfectly. In both cases the result is the same: failing to generalize to what? To the unseen test data. That is the ultimate disaster. Perfect. So, a good example, an illustrative example, let's go back to decision trees, okay? I want to show you the effect of noisy labels and insufficient data on the training experience, and I want to show you how it affects the decision tree. So look at here, we've got some examples here, two classes of examples. The red ones represent family car, and the yellow triangle ones they represent sport car. And we have two attributes here. One is car price in thousands of dollars, and the other one is the mileage, which is measured in units of 1,000 miles. Okay, now if I use a decision tree and ask it to divide my input space, these boundaries happen, right? So if you look at these little boundaries, both of these are the results of your decision tree, basically slicing up the input space. And the corresponding decision tree to this input space is this right here. So at the root of the tree we have car price, yeah? And we have chosen 3,000 as a threshold, yeah? If you follow this decision tree, you can figure out that we will eventually reach to 3 leaves here, yeah? For example, let me just traverse the tree once for you, and then you can just follow the other routes yourself. For example, car price bigger or equal to $3,000, yeah? So in case that's false, then we fall on the left-hand side of this line, right? And in that case, we are resorting to use mileage, okay? Now we're saying if it's larger than 4,000, which is this case, true. If it is true, we end up with family cars, okay? Because that represents this subspace over here, okay? And that is when we end up with a leaf node. Yeah, we have 2 family cars and 0 sport car, and the other routes are the same way. Now I want to explain the effect of noisy labels first. Let's go further. Imagine that these 2 guys right here are indeed noisy labels, meaning that they have the wrong labels, meaning that we thought they represent the family cars, but they actually don't. They're indeed sport cars, but our algorithm has learned them as family cars because that is what we told the poor guy, yeah? So we said these 2 guys are family cars, and that is what it learned, okay? Now, I want to show you how this will affect the testing experience. If you look at the red part of the whole input space, all these crooked red lines, that means the decision tree thinks that everything appearing on that area belongs to the family car, and anything belonging to the yellow area belongs to the sports car. Yeah, so in this case, we have this little unseen test data, and the question that we're going to ask our algorithm is this a sports car or is this a family car? And what happens is your algorithm is going to say, well, it is a family car because it falls in the red region. Yeah, but remember, the only reason that it thinks that this region is it belongs to the family cars is because of those two wrongly labeled data. Yeah, so if you think about it, this test data falls in the region where the car price is less than 3,000. For example, if you look at the tree, car price larger than 3,000, it is not true, so we jump to the false root over here. And then, is mileage larger than 4,000? Yes, it is. So we end up here, and this label over here, and we label this test data as the family car, which is not right. Now imagine if we denoise these labels, yeah? So we change those two and we correct them. So those two instances are now correctly labeled as sports car, yeah? And how does this change the training experience? As you can see, the algorithm only needs car price to be able to successfully divide the input space, yeah? Anything larger than 3,000 will fall under family car. Anything smaller than 3,000 will fall under sport car, and this is represented in the tree as well. So if you look at this corrected tree, we don't even need mileage to split anywhere in our tree. It is a much smaller tree and a corrected one. So we have car price larger than 3,000. If it is the case, the data would fall under the family car class, otherwise the sports car class. And that is how you can see that the corrected labels or the noisy label, how drastically it can change the perception of our algorithm with regard to the input space. Yes? Cool. Now, the other scenario where we have insufficient training data. Yeah? Now, let's say those two guys over there are not noisy labels, they're correctly labeled and everything's fine, but our training data is simply not enough. It doesn't represent the actual population, yeah? Now, this decision tree right here, it represents the trained decision tree that has used this data to be trained, okay? But I want to show you something. Actually, let me put it this way here. So all these little triangles and that blue circle, they are the missing data from our training data. Okay? They're not there in our training data, and our machine has no idea about that whatsoever. Yeah? So let's look at the tree. The tree thinks that anything that falls under this branch over here, meaning that car prices larger than 3,000 being true, anything that falls under that branch, which is this branch, this huge bit over here, should be classified as a family car. Yeah? Why does it think that way? It's because it doesn't have those data points in the blue circle in the training data. Yeah? It doesn't see anything in there. So it just assumes that anything in that region should belong to the family car. And indeed, this is how the tree perceives your input space. The red area is again for the family car. Now, if the test data, that unseen test data, happens somewhere there, somewhere in the area that our algorithm has not seen any data from, yeah, it hasn't seen anything up there, yeah. If a test data happens to be in that area, our algorithm is assuming that it's a family car data, and it's again wrong. Okay? Now, let's see if we correct our training data, what would happen, how our tree will change. There we go. Those little triangles have been added to the training data, and we have trained our algorithm from the beginning. Let's see how well, before I show you the tree, you can already see that the training, the input space has been divided into 1, 2, 3, 4 sub areas. Yeah, we have a different decision boundary now. Now, if we look at the tree, There we go, we have a different tree now. So car price being larger than 3,000, let's say that's true. We're gonna go to the left branch. If mileage is larger than 5,000, okay, so we're looking at this part, yeah, this little part over here, 5,000, so this line over here. If mileage is larger than that, it falls under this region, which if it's true, then we are classifying anything there as sports car, yeah? So that test data that had happened somewhere around here and we had classified that by mistake as a family car will now be correctly classified as a sports car, because our data is now more complete and a better representative of the actual population of family cars and sports cars. Yes? Perfect. Okay, that is great. So we covered the meaning of overfitting. We said that overfitting means that we will learn our training data absolutely perfectly. And the downside of that is that when it comes to generalizing our knowledge to the test data, we fail because we have basically, well, memorized our training data. And we showed you how memorizing a training data could harm our training experience. We showed that if our training data is noisy or insufficient, very, very incomplete, in both cases, we are going to suffer during testing. So I hope that this has been informative for you. In the next video, we're going to focus on how to address this issue, and some more issues about decision trees will come in the upcoming videos. If you're interested to know more about this idea, well, the link to the blog post of ML Done is in the description. Plus, if you want to follow us on LinkedIn or Twitter, the links to those are as well posted, as well as the Facebook link in the description. So you can just follow us, we'll be more the merrier. In the meantime, if this has been informative for you, I would encourage you to subscribe and also click on that little ring button over there so that you'll be notified when I upload new videos. So I hope that this has been informative for you. Thank you very much for your time and see you the next time. Bye-bye.